Hi everyone. Thanks for joining, and thanks to the organizers of Cosmology from Home for the opportunity to speak at this great conference. All right, let's get started. The plan for today is to talk about axions and the Axiverse. And a lot of people might be familiar with the string Axiverse. Today I'm going to be talking about an alternative scenario known as the field theory Axiverse. Let's get started. So axions have a long history dating back to the 1970s, starting with the strong CP problem of the standard model. And the one-liner story here is that by introducing this new field, you could dynamically set this CP violating phase to 0. And how this is achieved is by introducing a complex scalar, here I'm calling it capital Phi, where the axion is the phase. The axion is the Goldstone boson of a spontaneously broken global U1 symmetry, where here I have a Higgs potential for Phi. In the vacuum, pi picks up a VEV. This is the axion decay constant. Through non-proof effects in quantum field theory, I get some cosine potential, which breaks the shift symmetry of the Goldstone boson down to a periodic shift symmetry, generating a mass for the axion. The nice feature about axions, which is why we study them so much in cosmology, is that the mass is generated purely through non-perturbative effects. There's no perturbative loop corrections to the mass. And in this sense, it's technically natural to have a small mass for its axion field. So we can describe it in terms of this Klein-Gordon equation. This is the simple equation of motion for a scalar field. And our usual scenario is that initially the field is much lighter than Hubble and it's frozen in, and at some threshold time, the mass is of order Hubble, it rolls down its potential and starts to oscillate. And this provides a very simple minimal model for how to get the dark matter relic density. And there's lots of neat particle physics that comes along for the ride that follow from the characteristic couplings that this pseudoscalar field can have. This is axions in a nutshell. String theory gives us a ton of axions. And the simple story here is that gauge invariance in extra dimensions, which forbids an explicit mass term appearing for these gauge fields, under dimensional reduction leads to scalar fields with a shift symmetry. And the simplest example is to think of 5 dimensions where the 5th dimension is a circle. I do dimensional reduction of simple electromagnetism on a circle, and I end up with a scalar field that has an exact shift symmetry. So string theory has more than just electromagnetism. It has p-form fields, I have 4-form fields, I have multiple types of 2-form fields, and I have a C0 axion as well. So I have all these different gauge fields which could be giving me axions, and I have all these different dimensions that I can do dimensional reduction over. This leads to a huge range of possible masses and decay constants. And the approach usually taken is to try to make statistical predictions of the string landscape for what should be the axion mass and decay constants that we observe. And the growing consensus is that the statistical distribution should be roughly log uniform over a huge range of masses and decay constants. Now, this sounds like it should be really easy to get anything and everything that you want, but actually getting string cosmology from the string Axiverse is non-trivial at the least and difficult at times. And in particular, because often if you actually get into the details of moduli stabilization, often only 1 or 2 of these axions are light, or in particular ultralight. And this is borne out in studies, for example, of early dark energy by myself and collaborators, of fuzzy dark matter, that in particular, getting these extremely light fields with relatively large decay constants is really non-trivial in string theory. And amongst these different possibilities for the origin of the axion, it's really this C2 field, which seems like the best candidate for getting ultralight axions, such as fuzzy dark matter, in the context of string theory. So we really can't take ultralight axions for granted, even in the context of the string Axiverse. An alternative approach is to think about axions that arise instead of this global U1 symmetry breaking by some scalar, thinking about chiral symmetry breaking in a theory like QCD. So here I'm showing just the free Lagrangian for some quarks that are charged under some gauge field. And this theory enjoys a chiral symmetry breaking where I have NF flavors, different species of quark, and they can rotate into one another. And I have a separate SUN group for the left-handed fermions and one for the right-handed fermions. In the vacuum state of QCD, where I have a quark antiquark condensate, which is pairing up left and right degrees of freedom, this breaks that chiral symmetry. And it breaks, to be more specific, it breaks the left cross right chiral symmetry down to the diagonal subgroup, which we call the vector SUM. The Goldstone bosons of this chiral symmetry breaking is what we're referring to as the field theory Axiverse. And the field theory description, the effective field theory, is somewhat similar to your regular axion that you're familiar with, where here you can describe in terms of a complex scalar where the phase is this set of axions where they're being contracted with the generators of SUN. These are the tau A. You can work out what is the potential energy of these Goldstone bosons if I put in some mass matrix for the quarks. And if I have degenerate quark masses, I actually indeed end up with the cosine potential for the pions. So there's a very strong resemblance here between pions from chiral symmetry breaking and axions as we know and love. QCD also gives us a prediction for the mass of these fields. The Gell-Mann-Oakes-Renner relation tells you that the mass of a pion scales with the QCD scale and the sum of the quark masses contained within that pion. And the decay constant is anchored to the dark QCD scale. So as a minimal model building approach for thinking about constructions of the field theory Axiverse is to take, first of all, two energy scales. You have ultralight energy scale, which is the quark masses, and a high energy scale, which is the QCD scale. And if you have some dark Higgs or other fields, they have some energy scale benchmarked to that lambda dark QCD. And lambda dark QCD is going to give you your axion decay constant, which you need to be above, say, 10 to the 10, 10 to the 11 GeV to get nice axion dark matter. And you want the quark masses to be then ultralight, much less than EV, to make sure that these pions are really evolving as coherent scalar fields. To get a portal to the standard model, it's relatively easy. Just introduce a millicharge for the dark quarks. You can do this through kinetic mixing. And the scenario we have in mind here is that the dark photon doing the kinetic mixing is always heavy, anchored at the dark QCD scale. And this millicharge could in fact be anywhere from 10 to the minus infinity, say 0, up to 1. I mean, we can talk about this in the discussion section. Actually, there's no obstacle to having unit electric charge for these dark quarks because the charge is confined within hadrons, and the confinement scale of lambda dark QCD is high. So let's get to some minimal Axiverse constructions here. So the first one was put forward by myself and Azadeh Mahmoudjad in 2022, thinking about just a simple setup where I have an up and down quark, like the standard model up and down, and they have some millicharge under the standard model electromagnetism. And in the confining phase, this leads to one neutral pion and one charged pion. And they have masses, which are well known. The charged pion gets a correction due to its electric charge, which scales with QCD. So whether the charged pion is evolving like a coherent scalar really depends on this competition between the millicharge and the QCD scale. And I get couplings to the photons, both of the neutral pion, the pseudoscalar, and of the charged pions. We're going to ramp things up a little bit and go to, what if I have 6 flavors of quarks? Remember that the standard model has 6 flavors of quark. Let's consider, say again, let's split them up into 3 generations and let them have some parameters, specify their masses, parameters C1 to C6. And you can work out, it's a relatively straightforward group theory calculation to calculate the quark composition, and then from that, the mass of every pion in the theory. And you get, for NF equals 6, you get 5 what we usually refer to as neutral pions, and you get 9 charged pions. In the middle here, you also have kaons, which are these complex neutral states. So the kaon of the standard model, this is a complex neutral in the standard model. In this NF equals 6, where all 6 quarks are relatively light, you get actually 6 neutral complex fields. And I'll note that these expressions here, if I were to take degenerate quark masses, then the masses of these neutral pions would just be integer multiples of 1 benchmark scale. And the couplings here, you have your regular pseudoscalar coupling with some anomaly coefficient lambda 1 that you can usually work out from evaluating some triangle diagrams. The charged pions couple to the photon field, and the complex neutrals will couple to the field strength. And in principle, you can have favor violating currents and things like this. That depends on the details of how this Axiverse model is constructed. Most recently, in follow-up work with Stefan Alexander and Tucker Menton, we looked at the case of general number of flavors. And in this setup, you get, for NF flavors of quark, you have NF minus 1 pseudoscalar pions, and then scaling with NF squared, number of neutral complex scalars and charged complex scalars. So there's a lot of structure here to this Axiverse setup. Now let's turn to how to actually test these ideas, and let's start with the classic approach to detecting Axion-like particles, which is direct detection experiments looking for the decay into photons. So you can calculate the pion photon coupling, scales with the number of colors in your dark QCD, the millicharge parameter, and the decay constant, and an anomaly coefficient that's some order 1 number that you can calculate and find it. You can find it in our papers. In NF equals 6 case that I was showing previously, you have these 5 neutral pi pions, sometimes refer to them as pi axions. And this gives you, the characteristic feature here is it gives you multiple distinct but narrowly separated resonances. So if I have degenerate quark masses, they're really at 2, 3, 4, 5, 6 in order of 1 single shared mass scale. And if I do the simplest naive look at constraints, which is to say, let's just look at constraining these things one by one, not considering any integrated effect. This is what the constraint plots look like, and it's extremely sensitive to this millicharge parameter. So as I briefly mentioned before, if the millicharge parameter is order 1, then these charged pions have mass at the dark QCD scale. And the decay constant is also benchmarked at the dark QCD scale, and we need that quantity to be larger than 10 to the 11 GeV. So a scenario where epsilon is order 1 is a setup in which all charged degrees of freedom have masses 10 to the 13 GeV. These are super heavy particles, and they're not going to impact low energy phenomenology at all. And that's actually a separate interesting discussion about the super heavy dark matter aspects of this. I'll quickly note that there's also a parity-even portal, if I think of like pion squared, field strength squared, and you can probe this through things like atomic clocks. And so there's multiple complementary observational tests of this low energy spectrum of the field theory Axiverse. I'll also note that you can get fuzzy dark matter phenomenology out of this, and particularly multi-component fuzzy dark matter, which can give you things like boson stars or cores to dark matter halos, like in fuzzy dark matter classic. So in the simplest possible setup, you take non-relativistic limit, you find these 3 copies of the Schrodinger equation, where here I'm considering NF equals 2, just 2 flavors of quark. I get a neutral pion and a charged pion, and I decompose the charged pion into 2 degrees of freedom. These 3 in total scalar fields couple to gravity through the Poisson equation. And you can solve these equations disjointly to find what solitons look like. And an interesting feature that I would highlight is as I change the composition of a soliton. So if I say like, oh, the core of this dark matter halo is 50-50 between the charged and neutral pions, or the core in this halo is, for some reason, environmentally happens to be entirely neutral pions. I change the core radius of your of this soliton. So insofar as you can imagine that the composition in terms of how much of one ultralight axion component versus the other depends on environmental conditions, or locally, you have fluctuations of these fields throughout the universe, then this can lead to a diversity of dark matter halos, as opposed to one universal core radius mass relation. So let me end here and summarize the field theory Axiverse. The big picture is we're thinking about Axion-like particles that come from chiral symmetry breaking. The mass and decay constant, in this case, are set by the quark mass or quark masses and the QCD scale. This differs from the string Axiverse in some key ways. In particular, when you want to think about statistical predictions for masses and decay constants, in the field theory Axiverse, the simplest picture that emerges is a uniform distribution, versus in the string theory picture, what appears to be emerging is a log uniform distribution of masses and decay constants. I'd also note that in the field theory Axiverse here, there's only one non-perturbative effect at play, which is confinement in your dark QCD, and that leads to having one universal decay constant for the different pions. Versus in string theory, you have this sort of plethora of non-perturbative effects that you can play with, and this leads to a plethora of decay constants. You can get a unique decay constant, a unique mass for every axion in the game. So this one versus many decay constants distinguishes the string Axiverse and the field theory Axiverse as well. And I'll also emphasize there's lots more to the theory than just the Axion-like particles. And of course, this goes for string theory as well. In the field theory Axiverse, you have these complex neutral scalars and the charge scalars. And in addition, you also have the baryonic states of your dark QCD, which have masses of order the dark QCD scale, which again we're taking to be here 10 to the 11 GeV or greater. So these are really genuinely super heavy degrees of freedom. These are like wimpzillas, if you will. And super heavy dark matter has its own interesting phenomenology, which I'd love to talk about more. Okay, thanks everyone for joining. That's it for me.